This is the lecture for Tuesday, November 27th. Today we'll be talking about waves, specifically traveling waves. So let's first discuss what a wave is. It's a wave is a disturbance. You can think of water waves, you can think of sound waves, light waves. The basic thing we need to describe, though, is some sort of a displacement of some material. For example, if you think about waves on a string, if you have a piece of string, then you might have a displacement of the string. And so this capital D is my symbol that I will use for displacement. Now for a wave involves oscillations that we've already been talking about with simple harmonic motion, but the main difference is that we'll have this displacement, or these oscillations will happen, and we'll look at them versus position or distance, and we'll look at them versus time. So x here, this is measuring the distance or position. Either word is fine. And here's the displacement. And so I have some sine wave like this, d versus x. And if I take 2 points that are the same, the separation distance between these 2 points is what's called the wavelength. And the symbol for the wavelength is lambda. Okay, now, so let me write this out. Wavelength, lambda is the length for one cycle. This is similar to, this is analogous to period, which we call capital T, the time for one cycle. Okay. To make the comparison, if I were to draw the displacement d, and now this time I'm going to plot the time, t, and then I have an oscillation like this, then the time between two repetitions of the same position will be the period. Okay, so continuing on with this analogy, we had before something called the angular frequency. And we use the symbol omega. Now you should recall that the angular frequency could be written in terms of the period. So omega was equal to 2 pi divided by capital T. So this is angular frequency. And T is the period. Now, making the analogy between the period for time and the wavelength for position, we can define the analog of angular frequency. We can define the angular wave number, or just plain old wave number. And that has a symbol small k. Now, it's a little unfortunate that we're using, again, the symbol small k, because we use this for spring constant, but that's something we'll just have to deal with, because this is the standard symbol for wave number, angular wave number. And it's defined as 2 pi divided by lambda, the wavelength. So lambda is the wavelength. And this small k is the angular wave number. So don't confuse this with don't confuse this with spring constant. So if you're wondering how you can keep track whether it's spring constant or not, or a wave number, the simple rule is if there's no spring in the problem, it's not the spring constant. If there's a spring in the problem, it is the spring constant. So it's not that hard to, I think, figure it out. Small k in this instance is the angular wave number. So it's defined as 2 pi over lambda, just as we had omega is 2 pi over t. Okay, the units for the angular wave number, it's going to be radians divided by meters, or if you don't write radians out explicitly, it would just be inverse meters. Okay, if you have any questions, go ahead and ask the student that's supervising today's lecture. So we're going to be talking about traveling waves. By traveling wave, I mean something that actually moves in a very specific way. Okay, so the idea of a traveling wave is, suppose I have a little wave pulse, like this. So this is drawing position, and let's say this is x is equal to 0. So let's say this is a point on a string. Think of this as a pulse, wave pulse on a string. So this is, the wave is actually moving to the right like this. This is the wave motion. And by wave, by the pulse moving, I really mean, think about the actual wave is moving like this. The pulse is actually moving to the right. Okay. So as it moves like this, I can think about what's happening to this point on the string. So I'm going to draw, this will be the flow of time. This is the progression of time. Time progression. So a little bit later in time, the wave pulse will have moved over here. And so now this point on the string will have moved upwards. Now if I wait a little bit longer, the wave pulse is a little further along. Now it starts to move down. Okay, so the point on the string just moves up and down, but the coordinated movement of all these points on the string produces the fact that it looks like this pulse is moving. The pulse is moving to the right. Okay, so it's moving, continues to move to the right. Okay, so we can talk about the speed of the wave. So the speed of the wave is given by the formula v. So v is the wave speed. Sorry, going off the edge here. Sorry about doing that. Wave speed. V is equal to the wavelength times the frequency. Now, since the frequency is equal to 1 over t, the period, so that means we also have v is equal to lambda divided by the period. Okay? So t is period. So that's another equation. So the speed of the wave is v, and it's equal to lambda times f, or lambda divided by t. And let me try to convince you that this makes sense. So frequency, this is going to be number of cycles per second. Okay, cycles per second. And lambda the wavelength. I guess I don't really need the per here if I do cycles over seconds. And the wavelength is the number of meters per cycle. So if I multiply the number of meters per cycle times the number of cycles per second, then the cycles cancel out, and so that means lambda times f will be number of meters per second. Okay, that's how I think of this is how I think of the wave speed, multiplying the wavelength, which is the number of meters per cycle, multiplying it by the number of cycles per second to get number of meters per second. Okay, so we have these two formulas for the wave speed. Let me write down another formula. Okay, so we know the frequency is the angular frequency divided by 2 pi. And we also have that the angular wave number is 2 pi divided by lambda. Let me write down this in a different way, that lambda is equal to 2 pi divided by k. You cross multiply them, divide by k. Then let's take these two guys, put them together. When I multiply lambda times f, so I have v is equal to lambda times f, and that will be equal to 2 pi over k times omega divided by 2 pi. And cancel the 2 pi's, and I get omega over k. So I get that the wave speed is omega over k. Okay, so that's another formula for the wave speed without any 2 pi's involved. The next thing I want to talk about is how to write the traveling wave as a function of x and t. As a function of x and position and time. Okay, there are actually several ways to do it. So let me write down, this will be a traveling sine wave moving in the plus x direction. Okay, and I'll give you 3 different forms, and I'll try to explain why they're the same and what they mean. Okay, so the displacement d is a function of x and t. It's equal to the amplitude a, and instead of writing, so I'm going to write down a sine wave rather than a cosine wave, although one could write cosine as well, but the convention is for these traveling waves to write the sine function. So it'll be the sine of 2 pi over lambda times x minus 2 pi over the period times t. I'm going to explain where these factors come from, but just wait for a moment. Let me write down a different way of writing this. Okay, it's going to be the same formula, but I will pull out the factor of 2 pi over lambda in front, like this. So it'll be multiplied like this. And then I will multiply v times t like that. If I take 2 pi over lambda, multiply with v, distributing this product, I will end up getting exactly 2 pi over t. This follows from the fact that v is equal to lambda over t. So v is the wave speed. I can also write d, which is a function of x and t, as a times the sine of k times x minus omega times t. But that's another way of doing it, because k is 2 pi over lambda, omega is 2 pi over t. So all three of these functions are exactly the same. So all three of these describe a traveling wave, traveling sine wave with wavelength lambda, period t, and wave speed v, which is lambda over t, moving in the plus x direction. Okay, now as an aside, I'm going to mention that if we want a wave moving in the minus x direction, we write the following, either d of x of t. Okay, comparing with up here, we just replace the minus signs with plus signs. So this would be a sine 2 pi over lambda x plus 2 pi over t capital T, and 2 d of x of t, a sine 2 pi over lambda x plus v times t, or 3 d of x and t is a sine of kx plus omega t. Okay, so notice the minus x direction goes with plus signs here, whereas motion in the plus x direction goes with minus signs. I'll explain why this is that way a little later. As another aside, if we want a wave moving in the plus x direction with some arbitrary phase constant, so if we want a wave moving in the plus x direction with phase constant phi 0, then we have to just put this extra phase constant inside of the sine function. We have a sine 2 pi over lambda x minus 2 pi over t capital T times t plus phi 0, just tacked on the end here. Now we can write the second form, a sine of 2 pi over lambda x minus vt. We just tack on the extra phi 0. Or we have the third form, a sine of kx minus omega t plus phi 0. Okay. If you want to find what is phi 0 given some initial conditions, for example, suppose they tell you what the wave looks like at t equals 0, you would just set t equals to 0, then you would have a sine 2 pi over lambda x plus phi 0. You could use that to determine phi 0. So the initial conditions could give you the phase constant. Now let me try to make some sense of the basic formula we just wrote down. The basic one was this one here, from which we did all these extra examples. Okay? Let me try to explain first of all why there's this factor 2 pi over lambda multiplying x. Where did that come from? So why 2 pi over lambda times x? Okay, the idea is we want a wave with wavelength lambda. So note that when x increases by an amount lambda, 2 pi over lambda x increases by 2 pi over lambda times lambda, which is 2 pi, but that's equal to 1 cycle, 1 full cycle. Okay? So that's why this is what we want. It makes a wave with a wavelength of lambda. Now you might ask why 2 pi over capital T times t. The same sort of logic here. So when t, the time, increases by the period capital T, then 2 pi over capital T times t increases by 2 pi, which is equal to 1 cycle. Now you might then also ask, excuse me, why 2 pi over lambda x minus 2 pi over capital Tt? So why did we make the sine function have this combination? Okay, that may be a question you have. Hopefully the A out in front is simple. That's just giving you the amplitude. That's the maximum value of the displacement. But you may wonder why this combination inside the sine function. So what we'll do is we'll take a look at the point where 2 pi over lambda x minus 2 pi over t capital Tt is equal to 0. Okay, let's just focus on that point. Now when t is equal to 0, at the initial time t equals to 0, if we set this equation up and solve for x, we find that x is equal to 0. Now, if if t is greater than 0, then we can solve this equation. We get 2 pi over lambda x, bring this to the other side is equal to 2 pi over capital Tt. And so now what I can do is divide by 2 pi, and then multiply by lambda. X is equal to lambda over t capital Tt. For lambda over capital T, wavelength over period is the wave speed, so I get that x is equal to vt. So it starts off where this point is x equals to 0, but when time is greater than 0, x will be v times t. So this point where this argument of the sine function is 0, that point will move with the speed v. So this point moves with speed v. Okay. So what do we have here? We have here's the wave, like this. And this is the curve t for t equals to 0. Here's the displacement versus x. Okay. At t equals to 0, it looks like this. But at t non-zero, it has moved from here to there. And so this will be t greater than 0. And it's moved by amount v times t. So this change in x will be v times t. Shifts forward by amount v times t. Okay, if you have any questions about that, please ask the student that's supervising today's lecture. I will just finish today's lecture with a note that this is showing the forward movement plus x direction. So note the sine of 2 pi over lambda x minus 2 pi over capital Tt is moving in the plus x direction. So the plus x goes with the minus sign. Okay, whereas if I have sine of 2 pi over lambda x plus 2 pi over capital T small t, this guy is moving in the minus x direction. Okay, and the argument was exactly what I've written down here. With this minus sign in here, when I solve for the position of x for t greater than 0, I get a positive value of x. Right, so that's why the minus sign goes with a positive x motion, and the plus sign here goes with a negative x motion. Okay, if you have any questions about any of this, please ask the student supervisor in today's lecture. Otherwise, I'll see you guys on Wednesday.